Let's take a look at Chapter 10, which is the t-test for independent samples. To kind of refresh your memory on what independent means, let me give an example. If I roll a die, okay, and let's say that the first roll is 6, and I roll the die again, so second roll is 2. Okay, so if I knew on the second roll, if I knew that the first time was a 6, would that help me come up with a probability that the second one would be a 2? Okay, and the answer to that is no, and the reason is that these two rolls are independent events. In other words, knowing something about the first roll won't help me figure out what's going to happen on the second roll. Okay, in either case, the probability is 1 out of 6 for each roll. But if you take the example of choosing a card, so you have a deck of cards, okay, and I'm going to pull cards out and I'm not going to put them back. So if I pull on my first draw is a ace of hearts. The probability of pulling an ace of hearts is just 1 out of 52. Right? One card out of 52. But on my second draw, I know now that there's a reduced probability. In other words, there's not 52 cards anymore. So I don't put the card back. That means now the chance of drawing any card is going to have a probability of 1 out of 51. Okay, I know a lot of information, and so that can help me predict what's going to happen here. In other words, if one ace is gone, then I can only pull 3 now, 3 aces, and I've selected a heart, so that means there's only 12 out of 13, and so that influences how we come up with this number. And so that's this is an example of two things that aren't independent. So knowing what happens in the first draw definitely influences what's going to happen on the second draw. So for this t-test and independent samples, we're looking at two samples that don't influence one another. So the idea, maybe I'll just run through a kind of contrived example. Suppose we have we want to influence memory. So we have a particular treatment that we think is going to help people remember. So our treatment, let's just say that it's, I don't know, some drug. Okay, we think it's going to help, or some drug should help patients remember with memory. Okay, so we want to test this, and what we need to do is compare the results of people taking the drug. We need to compare those results with people not taking the drug. Okay, so what we're going to do, or maybe I should say one way to do this, is to have our population, so all people that could be potentially influenced by this, and what we're going to do is we're going to randomly select a group. Here's our big sample, and I'm going to write big sample here. And I should probably label this population. Okay, and then in our big sample, we're going to randomly allocate people to different groups. So I'm going to cut it in half, and this is going to be our control group, and this is going to be the treatment group. In other words, we've randomly allocated who goes to control and who goes to treatment. So in other words, we're not going to have a predisposition on who's going to take the drug or not. Anyone is equally likely to take it, and that's what we mean by independent. So these two groups came out of the same population. That's kind of an important idea, and so I'm going to write that. Both groups come from same, can't spell, same population. So with that comes our first big assumption. For the independent t-test, we have to be able to assume that the control group's variance and the treatment group's variance are equal. Okay, so let me write it like this. Big assumption is that the variance for the control group should equal the variance for the treatment group, the population variances. And the reason for this assumption, why it's so important, is that if we're going to compare these, we have to be comparing same-sized elements. So if this is your relative error, or not the relative error, this is the error from the center, we want both of them to have the same spread. So in other words, we're going to be comparing them, these two normal distributions, and we need them to have the same shape. Okay. Our next assumption, okay, is that both samples, well, maybe let me flip this. Both populations need to be normal. Okay, both populations need to be normal. Okay, they don't have to have the same mean, right? That part is essentially what we're going to be testing, but they have to both be normal. And the reason for this assumption is that we need, in order to use the t in general, we have to have normal population, and so here we need to have a normal distribution. So in order to guarantee that, what we're going to do is we're going to measure, or maybe I should phrase like this, the thing that we're going to measure with each group is we're going to measure the sample mean. So maybe I'll call this mean 1, mean 2. And what do you know about the sample mean? Well, if you have a large enough sample, then it will be distributed normally. Okay, that's what the central limit theorem gives us. So second assumption is that both populations need to be normal, and we'll guarantee that by taking our statistic will be the sample mean, okay, which is distributed normally. All right, so the big idea is we're going to compare the results from this trial. So we have some people in our control group, we have a certain sample size, and we calculate a certain mean. Okay, we look at the treatment group. They have a certain sample size and a certain sample mean. Okay, but remember that the purpose of using a t-test is because you don't know the population variance, and so each one of these control groups is going to have a a sample variance. So let me write it like this. Okay, and off to the side, I want to recall what the variance means, right? So variance is the sum of squares divided by the degrees of freedom. Okay, so when you use a t-test, you have to talk about the degrees of freedom, and this is an important thing. So each one of these control and the treatment groups, each one of these groups has a sum of squares. So let me follow up by saying sum of squares, and it has a degree of freedom. Oops, no, 2. All right. So we're going to use this information, and we want to conduct a hypothesis test. So before I do that, let me back up. The idea here is that the participants in each group, they don't know what they're getting. They don't know if they're getting the control group. They don't know if they're in the treatment group. So they're both going to receive, participants in either group are going to receive some pill. Maybe this one is a sugar pill, maybe it's something else, but it's not reactive or shouldn't be influencing the results. And the treatment is going to be the participants in the treatment group are going to be receiving whatever drug you think is going to help. So we start with the assumption maybe that our drug will influence, but maybe we should be safe and start with the assumption that our drug won't, be doing bad things, but we don't know. And so here are the assumptions. Okay, so our initial assumption to create this test, we start with an initial assumption that the population parameter for both groups are equal. So behind the scenes, we've already stated that the two population mean variances are the same. But what we're going to be testing, so we know this, or we are assuming this, but what we're really testing is to see whether the two means are equal. Okay, so a better way to write this, and more often we write it like this, that the difference between the parameters is 0. In other words, there's no difference. If we measure the average response to the treatment and the placebo, we should be seeing a net difference of 0. Okay, and we're going to test this against the alternative hypothesis that there is a difference between the two groups, and we actually write it like this. Okay, this would be for a two-tail. You might start with an assumption of a one tail, and you could follow up with something like, for the one direction test, you might say that mean 1 is greater than mean 2. In other words, the mean difference is bigger than 0. Or you might start with the assumption, the alternative assumption, that they're different in this direction, in which case, there you go. One of the things to consider in our case, this is the one we'd want to be able to test. In other words, if we know that our treatment does not negatively impact the participants, then we can do the one directional test and say, well, we should see an increase in memory or average response, and so we can do the one directional test. Okay, and we'll run through that in an example. Okay, so here are the hypotheses, but in order to run the test, we need to come up with a t statistic. Okay, so t statistic. Okay, and remember that t with degrees of freedom is equal to, in this case, well, let me back up here. T in general is always going to be listed as the data minus the hypothesized value, hypothesis, divided by the error. Okay, so this is going to be our sample values. These are what we're assuming is true, and then this is the error for that. So let's look at the t statistic for the two samples. So t with the degrees of freedom is going to equal the sample mean difference minus the population mean difference. In other words, the difference we should see, divided by the estimated sample error. Okay? So in order to address this t statistic, we need to talk about two things. First thing, we need to talk about degrees of freedom. Second thing we need to talk about is this estimated sample error. Estimated sample. Okay? Alright, so first let's talk about the degrees of freedom. Since we have two samples, we have different degrees of freedom for each sample, and they don't have to have equal sample size, by the way. We have two samples, but they come from the same population. So in other words, if we combine these two samples in our initial assumption, right, because our hypothesis test always starts with the initial assumption that there is no difference and the treatment does not have an effect, therefore either one of the groups is equally fine to use as a representative of the full group, we can look at degrees of freedom. So maybe I'll write total degrees of freedom should be equal to the sum of the degrees of freedom. Okay, and the reason for this one, we have two different samples and we throw out one, n1 minus 1. This one is n2 minus 1. So we're effectively throwing out two samples, and this is coming from the fact that we have two sample variances that we're measuring, and so we throw out one observation for the first sample and we throw out a second observation for this second sample. And so really the total degrees of freedom is just going to be the sum of the sample size, and then we throw out two, one for each sample error. Okay, the S, if you flip back here, the S1, if it goes, we throw out one for this one, and one observation for this standard sample error, and one for this sample error. Okay. Okay, this estimated sample error needs a little bit more work, and so let's revisit real quick the main assumptions. One, we have to have independent samples. Okay. Two, we have to have normal population for both, normally distributed for both, distributions for both. And then the third assumption is that the population variance have to be equal. Okay, we'll later talk about, I don't know what chapter now, we'll talk about testing things when the population variances aren't equal. Okay, but the idea here is that if they are equal, and if these are independent samples both coming from a normal distribution, we could then use either sample to estimate, right? So either sample standard deviation, we could use that to estimate the population standard deviation. And so what we're going to do is just combine all, combine the information from both samples and talk about it all together. And so the idea here is we have for variance, just to reiterate this, that it's the sum of squares divided by the divided by the degrees of freedom. So for the combined samples, since either one is equally valuable for estimating the population variance, we could say that our pooled standard deviation, so if I combine these samples, then our pooled estimate is going to equal the sum of squares from the first plus the sum of squares from the second divided by the degrees of freedom from the first plus degrees of freedom from the second. And really this just means the total sum of squares divided by the total degrees of freedom. Okay, so it's the same measurement that we've been using for our standard, or for our estimated variance. When you think about the estimated standard error, we have that standard error is the square root, so the variance, the square root of the variance over the square root of the sample size. Okay, so it's the standard deviation divided by the square root of the sample size. If you kind of back this up a little bit and look at standard error squared, this is then really the square of this, which should look like then s squared divided by n. And then when you take the square root, it's the square root of that. So really standard error looks like the square root of the variance divided by n, like that. Okay, so this is the model we're going to take, and since each one of the samples could be estimated by the combined standard error or standard deviation, we're going to just put that in for both. And so for the t statistic, the sample standard error for both, I'll write it like this, for both is going to look like the pooled variance divided by the individual sample plus the pooled variance divided by the independent sample, and then we're going to take the square root of the whole thing. Okay, and the kind of behind the scenes is that since these are independent samples, we can add up their standard errors and then take the square root of that. So this is the combined standard error for the difference. Okay, so just to reiterate, the degrees of freedom for the difference, let me get a good color here, the degrees of freedom is going to be the sum of the samples, throw away 2, and then the standard error for the difference, mean 1 minus mean 2, this is how the book writes it, which I write with a little d, is equal to, and then you take the square root of this pooled variance estimate scaled back by that sample, pooled variance estimate scaled back by that sample, where the pooled estimate is this total sum of squares divided by the total degrees of freedom. Okay? So what that means for us is that our t statistic with the degrees of freedom given, and maybe I'll just say df, and you know that I mean this one. Okay, it's going to equal the difference in our means, sample means, minus the assumed difference, and I'm just going to put it like this, but know that this will be 0. Okay, divided by this standard error measurement here, and I'm just going to write SD. Okay, so let's run through an example.